Here's another example of how to work out a problem, a physics problem using Newton's second law, and this is very similar to the one I did before. We're placing a 5 kilogram mass on an incline. This time the incline has friction, and everything else is the same, making an angle of 30 degrees with the horizontal. Rope is attached in a position over a pulley at the top of the incline. Then we hang a 6 kilogram mass on the free end of that rope on the other side, and they're asking what is the acceleration of the system. In this case, let's assume the friction or the coefficient of friction is 0.2. Again, we'll make a drawing to visualize what this problem is all about. So we have an incline. The angle theta is equal to 30 degrees. We place a mass on the incline. So let's call this mass 1. Let's say that's equal to 5 kilograms. And we hang a rope on that. We hang the rope over the pulley. The other side, we attach a 6 kilogram mass. Let's call that M2, and that's equal to 6 kilograms. In this case, we know that mu is equal to 0.2 friction between the mass 1 and the incline. And again, they're asking us, what is the acceleration of the whole system? So we work it out the exact same way. We establish all the forces acting on the system that are from external sources. We don't worry about the tension inside the system, although we can calculate that later after we figure out the acceleration. So what are some of the forces? Well, we have the weight of mass 2, m2g, caused by gravity, straight down. We have the weight caused by m1, which is also straight down, caused by gravity, m1g. But since it's on an incline, we're going to write the two components of that force. The one component, which is perpendicular to the incline, since this angle is theta, being the same angle as this angle theta right there, this becomes m1g cosine of theta. And then the component that's parallel to the incline becomes m1g sine of theta. Okay, that causes the m1g to effectively disappear. We've replaced it by its two components, so we no longer need that. We then also realize that the incline pushes back against the force perpendicular to the incline, m1g cosine theta, which is the normal force, which is equal in magnitude but opposite in direction to the m1g cosine theta. So this is equal to m1g cosine theta. That's the magnitude in the opposite direction. And then we have one more force to worry about, which is the force due to the friction between m1 and the surface. Now, we're going to assume that this mass is big enough to cause the whole system accelerate in this direction. In other words, we assume A will be in this direction. That will be our positive direction of motion. And the friction force typically opposes the direction that the whole system will move in or accelerate in without the friction, which means we can then assume that the force caused by friction will be directed downward. Force friction, which is equal to the normal force times the coefficient of friction by definition. And since the normal force causing this friction is equal to m1g cosine theta, we could say that the friction force is m1g cosine theta times mu. So now we have three forces. These two forces cancel out, so we have this force, and this force affecting the acceleration of the system. Now this force will be aiding in the acceleration. These two forces will be opposing the acceleration. That causes them to be in the negative direction and causes this force to be in the positive direction. So when we write the equation, F equals ma, and we then rearrange this equation so we have A equals F over m, understanding that F represents the net force on the system, only the forces that cause acceleration, and m represents the total mass of the system, so we write m sub t. Plugging in what those are, the net force will be the m2g, which aids acceleration, minus the m1g sine theta, which opposes acceleration, and minus the friction force, which also opposes acceleration, which is m1g cosine theta times mu. m1g cosine theta times mu, and that whole thing is divided by the sum of the two masses m1 plus m2. So here you can see that the net force on the system is the force caused by the weight of m2 aiding the acceleration, and then the two opposing forces subtracted from it, which is the weight along the incline of the first mass, and then the friction force also opposing that acceleration. So maybe to simplify the equation a little bit, I realize that every term has a g in it. I can factor out the g. So we have m2 minus m1 sine of theta minus m1 cosine of theta times mu, and then this whole numerator times g, all divided by m1 plus m2. All right, m2 is equal to 6 kilograms minus m1 is equal to 5 kilograms multiplied times the sine of 30 degrees, which, by the way, is 1/2, minus 5 kilograms times the cosine of 30 degrees, which is 0.866, times 0.2 for the coefficient of friction, and then this whole thing multiplied times g, which is 9.8 meters per second squared. And then we divide that by the sum of the two masses, which is 5 kilograms plus 6 kilograms. All right, now we grab for a calculator right here. Let's see what this is. So we have 5 times the cosine of 30 times 0.2. We subtract that from 6, and then we subtract from that 5 times the sine of 30, and then we take the whole thing and divide it by 11. And start over again. No.
Just start with where I have to do the G out. No, just start with the calculator part. Come on. Something like that. Come on.
My mind is not on this. Okay. Okay. All right, so plugging this into the calculator, we have 6 minus 5 times the sine of 30, which is 2.5, and subtract from that 5, so it's minus 5 times the cosine of 30 times 0.2, and divide that by 11, and then multiply the whole thing times 9.8, and the answer is 2.35 meters per second squared. All right, since we only had the numbers available to one significant figure, we should round this off to one significant figure, so we should say 2 meters per second squared, but at least you can see that that would be the correct answer if you were given the values of the masses to a greater number of significant figures. All right, now one more thing here. You may wonder, well, what's the tension in the string? Because quite often they ask for that. So let's say, what is the tension in the string? And if we take this portion of the problem right here, we then realize that the tension here is caused by the weight of this mass and the acceleration of the mass. And in this case, since the tension is not needed to pull the mass up, but less tension is required because the mass is accelerating down, we could then say that the tension in the string is equal to the weight, m2g, in this case, minus m2a. Now, if the mass had been accelerated upward, the tension would have been m2g plus m2a. But in this case, it's minus m2a. So, factoring out an m2, we get m2 times g minus a. And so m2 is equal to, in this case, 6 kilograms times g, which is 9.8 meters per second squared, minus 2.35 meters per second squared. And so subtracting that from 9.8 and multiply it times 6, the tension is 44.7 newtons. There we go. So that's how we calculate the tension. Now, of course, since this pulley has no mass and no friction, we can say that the tension on the other side on the string is also 44.7 newtons. Okay, and that's how you do those types of problems.